Data science is the field of extracting insights from data using a combination of statistics, programming, and domain knowledge. It involves collecting, cleaning, analyzing, visualizing, and interpreting data to solve real-world problems. It's used in industries like finance, healthcare, marketing, e-commerce, and artificial intelligence. Now, why is statistics critical for data science? Well, data science is not just about computing and coding. Understanding data is key, and statistics is the tool that makes sense of data. Therefore, data scientists must identify patterns, understand uncertainty, and quantify results, all of which rely on statistics. So, what is statistics? We'll give you our own definition, and we won't be bookish here. Statistics is about making sense of the world to see if there is an underlying order to the apparent chaos that one sees. Now, there might be no underlying order at all, as things might just be really random, but then again, well, maybe not, who knows? This question will be inherent in every statistical problem that one faces in real life. Is there really a relationship, or are we fooled by randomness? This will never go away, and we will live with this problem always, perhaps comforted by some probability numbers of whether we are right or wrong, which we shall talk about in the future. So for now, we will explore statistical concepts such as the mean, median, mode, and standard deviation from this perspective. These terms serve as tools to help us interpret and describe patterns in the world, providing us a structured way to understand apparent order. However, they should not be viewed in isolation. Rather, they must be considered collectively and within their proper context to derive meaningful insights. Okay, time for an example. Let's say we have two groups, set A and set B, as shown here, and we measured the weights and found out the following. So we have these questions. Number one, which set is heavier, set A or set B? For question 1, this is all a matter of summing up all the weights and finding out which set weighs more. And we know that here set A is equal to 821 and set B is equal to 831. So that answer is set B. Set B is heavier cumulatively. Now question number 2, which set has the heaviest individual, set A or set B? How about the lightest? Well, for question 2, set A has the heaviest participants at 180 and 150 pounds respectively. On the other hand, set B has the lightest participant at 25 pounds. Okay, that's so easy for now. Now, which set is heavier on an average individual basis? Now, for question 3, we come up with our first real issue. Who do we pick as the average individual from set A and from set B? Meaning, who should represent set A? Participant 9? Participant 8? Who should represent set B? Participant 10? How do we decide who to represent the two sets? This is not as straightforward as it would seem. It turns out the whole idea of who should represent set A and set B can be challenging and goes to the heart of a research problem who is considered an average participant, in this case, to represent the sets. Now, what if we randomly draw lots, one from each set? Is that a fair way of representing each set? In statistics, this is an issue of sampling, of how to get samples from each set. And we should note that the way we sample the sets can very well determine the outcome of our research and can introduce bias. This is really problematic if getting data is hard in the first place. So what if we just get the heaviest from each? In this case, however, is the heaviest truly representative of each set when there are really outliers or extremes not representative at all of each set? By the way, in statistics, therefore, we need to take a look at extremes and outliers, which tend to distort the sense of representativeness of an item from a set. In this case, this is an issue of dispersion clouding the issue of representativeness. We shall get back to this issue later. So in general, we choose the middle ground as representative of each set so that outliers or extreme numbers don't warp the sense of representativeness of a chosen participant. In statistics, this sense of middle ground is called the measures of central tendency, meaning we say that the middle is the representative. If we sort everybody out, then get the middle of the pack, then this is called the median. In this case of ordering, there are 10 participants per set. So there are 2 participants in the middle of each set. So just count to 5 from both sides in the ordering to get the middle. And for set A, those are 64 pounds and 82 pounds. And for set B, that's 81 pounds and 94 pounds. However, we may want to fine-tune this more and get the mean of those numbers and say that the middle of these two numbers will represent the real median. So that for set A, that will be 73 pounds, and set B, that's going to be 87.5 pounds. In this case, we say that based on the median, the average individual is heavier in set B than set A, given these two medians. Now, in the previous example, we said get the mean, which just says that we should just add the two numbers, then divide by the count of 2. We can extend this for all the numbers in each set rather than just the two middle of the pack numbers. We can sum it all up, then divide by 10, since each set has 10 participants. In this case, we have the following. Set A, 82.1, and set B, 83.1. That's going to be the means of set A and set B. This indicates that the average participant in set B is heavier than the average participant in set A based on the mean. Now you might say, hang on, there's nobody with those weights among the participants. Nobody weighs 73 pounds or 82.1 pounds in set A, and nobody weighs 87.5 pounds or 83.1 pounds in set B. So why don't we choose the number that actually appears the most frequent and make that the representative from each group? Indeed, if that exists, then it's called the mode, which is considered another measure of central tendency, and that will be 29 for set A and 120 for set B. So going back to the original question, it was, on average, which set is heavier on an individual basis? It turns out there are different answers as to what an average is, whether one considers the median, the mean, or the mode. The point we're trying to make here is that just knowing the statistical terms per se is not as helpful on a standalone basis, and we must answer a research question contextually based on the problem at hand rather than strictly giving the statistics as if it made sense in a vacuum. This is particularly true for data science, as there is normally a problem that needs to be addressed, a decision that needs to be made, so there must be some rhyme or reason to the decision making. In this case, while the statistics is a necessary first step, it's not the end all and be all of the analysis, and things have to be understood within the context of the problem at hand. In real life, there are situations where the mean, median, and mode are the same thing. So these measures of central tendency indicate a strong center of a dataset, and it does not matter what you use. At other times, they might be different, and in a lot of cases, the mean is often used because of a well-developed statistical literature that uses it heavily alongside measures of dispersion. We shall now go to that topic. Measures of dispersion. Okay, so let's say we already have the measures of central tendency to choose a representative of the set. As we have seen in our previous example, the problem with the center as a representative is that one may be more dispersed than the other, even if they have the same center. So the more concentrated a set is around its center, the more quote-unquote representative that center is to represent everybody else. Take a look at this example, set C and set D. In this case, both have a center of 5, but set C is more dispersed than set D. So we can say that 5 represents all items in D better compared to that of C. given these tighter dispersion, even if for all intents and purposes, both sets have the same center at 5. So this takes us to the measure of dispersion, core concept called the range versus average dispersion. We can take a look at the range of numbers, which is really just the maximum versus the minimum of a set. Going back to our first example, we have the following set. In this case, we know that the range in set A is bigger or wider than the range in set B, which gives us the idea that set A is more dispersed than B, which further implies that on average, the center of A is a poorer representative of everybody in set A than is the center of B relative to the center of B and everybody else in set B. That makes sense on the aggregate level, but it's not clear how that holds in terms of average dispersion. So let's replace each item in set A and set B by their means, then find out the dispersion on average. So we replace each number by its mean, then get the relative errors that arise from each replacement. We will have the following. It is clear that we cannot get the average replacement error if we try to get the average dispersion by summing up all the errors and then divide by n. Why? Because the errors sum up to 0. This happens because the mean is exactly the center, such that on average, the overcounts will exactly offset the undercounts, leading always to a sum of 0. That is always true. Well, there are ways to go around this problem, but there is an extensive literature on what's called the standard deviation, and we will focus on this literature instead as a measure of average dispersion. So one way to solve the problem of average dispersion is by making all numbers positive so that there won't be offsets at all. And this can be done by squaring the replacement errors, making everything positive, then getting the mean of the squared deviations rather than just getting the mean of the errors. So here we're getting the mean of the squared deviations. And in statistics, this is called the variance. So the variance is the sum of all of the squared errors, then divide by n. So it's the measure of the average squared errors. In this case, set A is more dispersed on average than set B as measured by the variance. However, the problem with the variance is that it uses square units, and we need to go back to the basic measurement. For example, if you're working on meters, then you'll have squared meters. So in this case, we simply take the square root of the variance to come up with what's called the standard deviation. So note, it helps to visualize what these statistical terms mean rather than just memorizing the formulas. So again, average of the squared deviations, that'll be your variance. Then you get the square root, that'll get you your standard deviation. So now we have the statistical table of the weights. Somebody looking at this table but without taking a look at the original data can immediately grasp that those in set B are heavier on average than set A, and that the data is more dispersed in set A than in set B. This is what we mean by making sense of the world, or making sense of the data. Now, what are some real-world problems that you might encounter that makes you think about how to use and analyze the data? Well, what if the problem is recruiting people from this group such that nobody goes over the maximum weight limit of, say, 145 pounds? Then obviously you won't use the averages, but rather look at the maximum weights and choose the group where everybody passes. Now, for this kind of data size, it's relatively easy to go over the data. But what if you had hundreds or even thousands or even hundreds of thousands of data? Then the so-called data visualization activities would be more helpful than just using the actual computed statistics. And this may include box and whisker plots, histograms, scatter plots, etc. For now, we will just focus on box and whisker plots. A box and whisker plot is a special kind of graph that helps us understand a group of numbers. It's like a picture that shows how the numbers are spread out. So in Excel, you can see all of this. The box This shows where most of the numbers are. It's like a box that holds the middle numbers ranging from 25% to 75% of the data as a range from smallest to largest. Then there's a line inside that box. This line is called the median. It's the middle number when all the numbers are lined up from smallest to largest. Then the whiskers, these are the lines that stick out from the box. They show where the rest of the numbers are even if they're far away from the box. And then there's an X. This shows where the mean is for comparison with the median. So box and whisker plots are helpful because they give us a quick look of how spread out the numbers are and where the middle is. It's like a snapshot of all the numbers. If you hover on particular points of the chart in Excel, it'll show the computed numbers as shown here. As can be noted in the chart, the mean of both sets are nearly the same visually. So the question might be, the means are mathematically different, but are they also statistically different or are they the same? In this case, this would require a test of hypothesis and is widely used in statistics and will be dealt with in future lessons.